All right, guys, we've got the test 3 coming up, um, all about sequences and series, mostly series. So, going to do a little problem session for you guys. Almost all the problems I'm going to do today are going to be 11.6. Um, for studying for the test, you need to know the concepts from all these sections, 11.1 through 11.6. There's nothing new in 11.7, but 11.7 has a lot of really good problems. And then also, the only problem with 11.7 is it doesn't ask about absolute convergence or um, conditional convergence. So definitely review 11.6 as well. So if I was going to be studying for the test and working problems, I would really prioritize these two sections and then also mix in some of the other sections just for more focused review. Um, and some 11.1 as well. So I don't think either of these sections cover 11.1. Okay, so there's some important stuff from each section. Like 11.1 is all sequences, right? And then the other sections don't really talk about sequences too much. So we need 11.1, and then also 11.2. This talks about sums of geometric series and telescoping series. Okay, so we need that. Okay, so a little bit of everything, but really 11.7, 11.6, you should hit those pretty heavy. So I'll start with some problems from 11.7, just going numerically as much as I can. Okay, so one I'm going to talk through before, a lot of the other ones I'll just show the solution. One I want to talk through because it's comparison test problem, and I feel like that needs the most help. Okay, so whenever I see polynomial over polynomial, I think comparison test. So I'm going to try the direct comparison, the regular comparison test first. Okay, so let's see. If I was going to compare this series to something, what would I compare it to? I would try and compare it to, let's see, I got n squared minus 1 over n cubed plus 1. I'm going to focus on what's important. I'm going to try and compare it to n squared over n cubed. I'm going to take the highest power on top and bottom, okay, and forget everything else. Okay, so I ignore the minus 1, plus 1. Okay, so I'm looking at this series, which simplifies to 1 over n. I know that's divergent. So remember, I'm trying to use comparison test here. So what do I need? I need my two conditions. Everything's non-negative. So if this is my ANs and this is my, I can use either one. Let's use this one. Okay. I need AN, BN, everything greater than 0. Yeah, that's true. Okay. Second, I need, if I want to show this is divergent, what do I need? I need it's greater than or equal to this. So do I have the inequality? That's the problem. Okay. 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 So what's bigger? Let's see. The numerator's smaller over here. Okay. So this numerator is smaller than this numerator. And this, I'm dividing by a larger number over here. Okay. So this inequality is going to be going this way. Okay. This thing is bigger than this thing. Okay. So if this series is divergent, remember what comparison test tells us in this circumstance? It tells us nothing, right? Okay, this is divergent. That doesn't tell us anything about that. So comparison test is failing. So remember, if you watched my video, what happens when I have the inequality going the wrong way? I should use limit comparison test. So what do I need? I need limit AN over BN equals some C strictly greater than 0. If this is true, these series are going to do the same thing. So if one diverges, the other is going to diverge. So let's figure out what this is. Okay. What's my A? This is my AN, this is my BN. So AN over BN is going to be okay, so this is my AN over BN after I simplify everything. So I need to figure out what the limit of this is. Polynomial over polynomial, highest power over highest power, coefficient over coefficient. Limit's going to be 1. Okay. So that tells me these two series are going to do the same thing. All right. I know this one diverges, so that means my original series diverges. Now I need to write everything up. Okay, so this is all my scratch work. Now this is maybe the most critical part and what I want you guys to focus on. I would say, let's say AN equals, or maybe our series AN equals my original series BN equals, okay, limit AN over BN equals 1. Series BN diverges, and usually say why. You could say in this case because it's the harmonic series. So series AN diverges, and again, we need to say why. It's not enough to say just diverges. We need to say by limit comparison test. Okay, so this work that we did, all this work we did, that's good and necessary, but we really need this last square. Okay, this is maybe, I'm not going to say the most important, but as equally as important as this. Okay, if you don't have this conclusion, then you're not getting full credit. All right, boom, number 2. So we're given this series again, we're just asked whether it converges or diverges. Okay, so again, I have polynomial over polynomial. That makes me think comparison test. So what do I compare it to? I simplify this term as much as possible to n over n cubed, which again simplifies to 1 over n squared. That I know converges by p-test, right? 2 is greater than 1, so it converges. Okay, so that makes me think my original converges, but I need to check my comparison test. All right, so what are my 2 conditions? I need everything's greater than or equal to 0. Okay, so looking at this, okay, it's going to be 0 when n equals 1, but then it's going to get bigger. Or then it's going to be always greater than or equal to 0. Then same thing over here. This thing's always greater than n equal to 0. Okay, that's fine. And number 2, the inequality. Here, the inequality is, obvious to me. Not to say it's easy, but there's not a lot to do here except write this inequality, okay? For something more complicated with maybe e's and ln's, maybe you got to do something, maybe you got to justify this inequality a little bit, but there's not a lot to do, not a lot to justify here other than just writing this inequality, okay? So I check that inequality, good. All right. Then how do I wrap up? This is my wrap up. Okay. So again, this is an important part. The series 1 over n squared is convergent by p-test. So our original series n minus 1 over n cubed plus 1 convergent by comparison test. Again, if I don't have these words, this whole wrap up, you're losing points. All right. So we definitely need some line like this. All right, onward. Okay, so problem 3, I see an alternating sign. I immediately think I should try alternating series test. So what am I can do? 2 conditions. First, I need the numerical part to be decreasing. Okay, so I need this part to be decreasing. AN plus 1 is less than or equal to AN. Okay, this one, it would be kind of a bear, actually. I would have to turn this into a function of x, take the derivative, and show that derivative is negative after a certain point. Okay, I worked this out on the side. It's pretty rough. I wouldn't ask you to do anything like that on the test. Be aware it could pop up on the final. So we'll cover that more as it comes up, I think. But on this test 3, I wouldn't worry about it too much. But maybe give some sort of short justification, like you could say n cubed grows faster than n squared, so eventually decreasing. Something like that. So very informal. Okay. What's the second condition? We need limit an equals 0. This should be more straightforward, and you should show this more rigorously. Okay, so again, it's not too bad. We know limit n squared minus 1 over n cubed plus 1. I got a higher power of n on the bottom. Okay, we know that equals 0. Okay, so I've shown my two conditions. Boom. I got decreasing and I got limit equals 0. Okay, so that's all I need for alternating series test, right? So I need my wrap up. I say -1 to the n squared minus 1 over n cubed plus 1 converges by alternating series test. Okay, moving on. Okay, number 4 is a good counterexample to number 3. Okay, so try this if you haven't already. Okay, so again, I see the alternating sign term. That makes me think alternating series test. Okay, so what do? I need to check my conditions. An plus 1 less than or equal to an, and 2, I need limit an equals 0. Okay, so let's start with 2. Okay, so let's see. If we started with 1, would it be decreasing? Actually, probably not. But number 2 is easier to show. So remember, if one doesn't hold, we still don't know what's going on. If 2 doesn't hold, we can make a conclusion. All right. So let's see. What's the limit of an? Okay. What is the limit of n squared minus 1 over n squared plus 1? Okay. Same power of n on top and bottom. Okay. So that limit equals 1. All right. So the limit of the stuff inside of these terms doesn't go to 0. So what do I know? This series has to be convergent. Series is divergent. But why? I do not say by alternating series test. I say and then if I wanted to be specific, I can say since limit an does not equal 0. Okay. So by divergence test, it's not divergent by alternating series test, it is divergent by divergence test. Okay. So just remember, alternating series test only tells us if something's convergent. Okay. It doesn't tell us if the series is divergent. To show it's divergent, we would need to use divergence test. All right, coming to number 5, we got e to the power n over n squared. I'm going to try ratio test on this one. You might ask why. Okay, when I see something kind of abnormal, maybe like something I'm not used to working with, okay, like e, I either think ratio, like the ratio test root test, or I think integral test. Okay, so comparison tests are usually going to be polynomials, or maybe like some trigs of polynomials would be comparison tests, things like that. For this kind of weird stuff, I try and use ratio test or integral test first. So here I went with ratio test. So I did an plus 1 over an. Okay, that's what I'm looking for. Okay, so I do e to the n plus 1 power over n plus 1 squared divided by e to the n over n squared. Okay, and I should end up with this here. Okay, once I simplify. And then I want to look at the limit of this. Okay, so here's where some skills with 11.1 can come in, these limit laws. I can bring the e outside the limit. Okay, and then I'm looking at what's the limit of this stuff inside. Okay, n squared over n plus 1 squared. That limit's equal to 1. So e times that limit is equal to e. Okay, and we know e is greater than 1. So when I do ratio test, I get a limit, I get a number. The limit is greater than 1. So what does ratio test tells me? It tells me that my series is divergent. So I write my conclusion here. Series is divergent by ratio test. All right. Number 6, I see n to the power of 2n over 1 plus n to the power of 3n. I got exponents with both exponents have n in them. that makes me think root test. Okay, that's not the only time you can use root test, but if you see something like this where, okay, everything's to a power of n, you should definitely think root test. All right. So what do I need for root test? I need to do the nth root of the absolute value of an. So everything's positive here, so the absolute value doesn't change anything. Okay, everything's positive, so it doesn't affect anything at all. So what's my an? The an is just this stuff. Okay, so I rewrite my an inside my nth root. When I take the nth root, remember that this n is going to cancel with these n's. Okay, so once I take the nth root, I'm just left with n squared over 1 plus n cubed. All right, and then for root test, I want to take the limit as n goes to infinity of nth root of an. Okay, so that limit is this limit, n squared over 1 plus n cubed. I have a higher power of n on the bottom, so I know this limit's going to 0. Okay, so what does my root test tell me? When the limit is less than 1, my series is going to be convergent. It's actually going to be absolutely convergent, right? And let's see, on the previous problem, it should have been the same. No, we had divergent on the previous problem. Okay, so that's fine. So yeah, our series is actually absolutely convergent. But remember, when a series is absolutely convergent, that means it is convergent. Okay, so if you were writing out the answer, the question only asks whether it's convergent or divergent. I would accept probably either one, but I mean, if you wanted to be 100% thorough, okay, how I would say this formally is I would say the series is absolutely convergent by the root test, so convergent. Okay, so it's both. Okay, but our root test tells us something's absolutely convergent, and then we go on to say, okay, well, if something's absolutely convergent, it's also convergent. Okay. All right, moving on. Okay, number 7. Again, going back to what I said when I have maybe something a little bit weird that I'm not used to working with, like e's and ln's. What should I could try a ratio test, root test, or maybe integral test. That's another good one. Okay, so this one's a good one for the integral test. I turn it into an improper integral. The integral is always going to have the same bounds as my series. So since my series goes from 1 to infinity, my integral goes from 1 to infinity. Remember, when we have this improper integral, we need to turn that into a limit, and then I need to solve the integral. Okay, so forget about the limit for a second. Just look at this integral. Okay, how would I solve this integral? This is a simple u substitution integral. U equals ln of x. Okay, so when I make that substitution, that x is going to cancel. I'm just going to have u to the -1/2. Okay, then it's just integrating. Okay, and I get this improper, this antiderivative. And then I undo my substitution. Okay, so when I undo my substitution, I get this for my antiderivative, 2 square root ln of x, or 2 ln of x to the power 1/2, same thing. Then I'm taking the limit as t goes to infinity for my upper bound, and then 1's my lower bound. So note when I plug 1 into this, ln of 1 is 0, square root of 0 is 0. Okay, so this is what I get when I plug in my t, and then this is what I get when I plug in my 1. And then I'm trying to figure out what's going on here. Nothing's changing as t goes to infinity here. What's going on here? Well, as t goes to infinity, ln of t goes to infinity, and then taking the square root of infinity is infinity. Okay, so the limit equals infinity. Since the integral is divergent, the series is divergent by the integral test. Okay, so this is my conclusion. You need to write this. Okay, so I see number 8. I see an alternating term, so maybe that makes me think alternating series at first. But I get the impression, let's see, unless I know some stuff about 4 to the n, maybe showing that limit is equal to 0 would be hard. So what's maybe a better way to go about this? Okay, so I see something I'm not used to, right? This 4 to the n. Okay, so something kind of weird. All right, so what did I say a couple minutes ago? When I see that, maybe I want to try integral test, ratio test, root test, ratio test. Let's stick with ratio test, right? It's very powerful. Okay. So let's try ratio test. All right, so what would I need? I would need n plus 1 to the fourth over 4n plus 1. Okay, that would be my an plus 1 term, right? I need to divide by an. And since I'm doing absolute values, I can ignore this changing sign, this -1. Okay. Okay, so I'm dividing by an, which is same as multiplying by the reciprocal. So that would be 4 to the n over n to the fourth. Okay. And then I'm simplifying. Okay, so 4n over 4n plus 1, it's 1 over 4. N plus 1 to the fourth over n to the fourth. Okay. So this is my an plus 1 over an. And now I want to take the limit of that. Okay, and what is this limit? Maybe you can see already, it's going to be 1/4, right? The limit of this stuff is going to go to 1, and then I got multiplied by 1/4. Okay, so my limit's 1/4, which is definitely less than 1. So my series is absolutely convergent. That means this, meaning this series is absolutely convergent. And what do I know about absolutely convergent series? They're also convergent. So I would say -1 to the n minus 1, n to the fourth over 4 to the n. Okay, my series is absolutely convergent by ratio test. So it is convergent. Okay. And I think that this saying absolutely convergent, so it's convergent, is more important on this one than on the previous one, because we actually have negative terms here. If we go back, let's see, to look at this one, no, not this one, this one, everything was positive, right? So we didn't have any negative terms. So absolutely convergent in this case, okay, is the same as convergent. I take the absolute values, they're convergent. It's the same thing as my original series being convergent. But now here in this case, there's a difference, right? The original series is different than the series of absolute values. So now it's more important to say, okay, it's absolutely convergent by ratio test, so it is convergent. Okay, moving on. All right, number 9, I got, it's alternating series, but it is got a factorial in it. So factorial always makes me think ratio tests, not that that's the only way to solve it, and maybe that shouldn't be the way we solve it every time, but usually. So I see factorial, I think ratio test. The thing you got to be careful with this is when we plug in n plus 1 for our ratio test, we got to be careful. Okay, so let's look at the numerator first. I replace n with n plus 1, right? But this 2 is going to distribute. So I should get pi to the power of 2n plus 2. Same thing on the factorial. When I replace n with n plus 1, I'm going to end up with 2n plus 2 in the factorial. Okay, and then I'm dividing by an, which means multiplying by the reciprocal. Simplifying factorials, if you need help on that, see my video on simplifying factorials. It's like 8 minutes. Okay, so that factorial simplifies to this. And then pi to the 2n plus 2 over pi to the 2n simplifies as pi squared. Now I want to look at the limit of an plus 1 over an, which is going to be the limit of this thing. And that limit's equal to 0. I know it looks like a C, but that is supposed to be a 0. Okay, so what does that tell us? What does ratio test tell us? It tells us that this series is absolutely convergent. And again, since there's negative signs in here, okay, absolutely convergent, we need to say implies convergent. Okay, so this series is convergent. Okay, so I'm getting tired, so this is my last one, and I just kind of sketched it out, but it should be good. Series n squared e to the power of negative n cubed. So again, I got some weird stuff in here. Maybe it's not the standard polynomial trig stuff, so that makes me think, what, either ratio test, root test, integral test, something like that, one of these tools. So if I look at this a bit closer, and I kind of mentally turn this summation sign into an integral, I know I can integrate that, right? I got e to the negative n cubed times n squared. I know if I do a u substitution, I can integrate this. Okay, so that makes me think I should try and do integral test. I can integrate it, so um, whatever the integral tells me is going to go for the series. All right. So I tried the integral, and this is kind of where I, skip some steps and tried some mental math. So if this is wrong, let me know. But I think it should be, uh, once we do our u substitution, we would get a 1/3, and then the derivative would be negative e to the negative x cubed from t to 1. And then we evaluate that limit, and we should get positive 1/3e. Okay, so again, check me on that. Okay. And then let's see, that means this integral is convergent. So my series should be convergent by integral test. All right. So again, let me know if I'm wrong on that, but as long as this integral is convergent, our series is convergent. They're not going to converge to the same number, but they'll both be convergent. All right. More problems to come, but I'm going to take a break for the rest of the night.